This is Maria Chekhova's hat. A perfectly normal object if your definition of normal involves scientists and questionable headgear traditions. In Germany, people do not simply say congratulations for a PhD or a big research grant. They build a shrine for your head, a hat. So Maria's research group crafted this one when they got an ERC grant.
Usually such hats have installations related to the interest. So in my case, for instance, there are mushrooms, and this is the subject of the ERC grant. This is a metasurface. These are photon triplets. And there are other things like my car and a book that I have translated and books that I read. Skis, because I like skiing.
But enough about hats. The real story is not what sits on the head, but what simmers inside. Human inventions. We travel to a place where brains bubble like lava and ideas sprout like mushrooms after it rains. Here lies Maria Chekhova's lab. Inside, everything revolves around quantum physics, the part of reality that behaves like it's written by absurdist playwrights. But what actually happens here, day after day, behind the closed doors of the laser labs?
We are trying to study the quantum properties of the light.
Sources of light which behave differently from what are the usual ones.
We detect them and we use them.
Basically, we try to feed our curiosity.
We generate quantum light.
Wait, quantum light? What makes it quantum? A classic example is photon pairs from parametric down conversion, where one photon splits into two lower energy offspring that remain entangled closer than twins in a distinctly quantum way. This is an ERC project called Multifunctional Flat Quantum Sources. In this project, they develop sources of quantum light, of photon pairs, and of squeezed light that are very thin.
Very thin layers of nonlinear crystals, or metasurfaces, or even cells filled with liquid crystal. Normally, the momentum conservation condition that tells that the momentum of the pump photon should be equal to the sum of momentums of the daughter photons does not have to hold here, because the source is very thin.
Imagine a soap bubble, a tiny shimmering film, just a few hundred nanometers thick, about the size of the light waves hitting it. Because its thickness is on the scale of the light's wavelength, different colors interfere, cancel, and reinforce each other. And that is why every bubble turns into a portable rainbow. Now shrink that idea down and apply it to photonics. Extremely thin films can be used as efficient factories for photons using spontaneous parametric down conversion.
The processes that are normally used in quantum light generation work with delta KL. So, since we want enough light, we work with very big crystals. So if we go from bulk crystals to very thin layers, minimizing this L, we can achieve delta KL tending to 0 for conditions that would be impossible to observe for the standard bulk crystals.
We then leave thin films behind and step onto something even stranger: metasurfaces.
Metasurfaces are basically these patterned or periodic array of very, very small structures. And metasurfaces are actually very versatile in the sense that you can generate many different kinds of photon pairs in different ways. So like you can generate photon pairs with optical angular momentums, you can generate photon pairs with polarization dependence, you can also generate entanglement, which is very important for quantum information and quantum optics. And these metasurfaces are basically the heart of the engineering these quantum effects.
Metasurfaces are arrangements of nanoparticles. Nanoparticles are periodically placed on a flat surface, and according to their size and according to the distance between them, they reflect or transmit different colors of light.
Nature, of course, did it first. The dazzling colors of some butterfly wings do not come from pigments, but from tiny structures whose dimensions are comparable to the wavelength of light, turning their surface into a metasurface painted in structural rainbows. Last but not least, the liquid crystals come on stage. A liquid whose molecules are very stretched, and so they can be oriented by an electric field tending to align along it. They are called crystals because there is a certain order in the neighborhood of a single molecule.
In my project, we're using some platform for generating some quantum states, and it's called liquid crystal. They can be rearranged by applying the electric field, external electric field, and for example, if you generate something in one polarization mode, you apply electric field, you completely rearrange liquid crystal inside the sample, and will generate in completely different polarization mode.
We have a lot of goals here. We need to enhance the efficiency of quantum light generation. We need to pass from photon pairs to squeezed light. We need to implement a new nonlinear process, third order parametric down conversion, when not a pair is generated but a triplet of photons. We want to convert the frequency of the photon pairs or one photon of a pair in the same nonlinear material. And finally, we want to couple emission of single photons by quantum dots, for instance, with the pair emission process.
I think nobody really understands how quantum physics works. It's why it's really exciting to work with it, because we want to discover something more. It's an aspect of reality which is really counterintuitive sometimes, but it's reality, so we want to understand what is happening.
What do you mean by how it works? If it works? It works. It works, yes. It works.
Do you fully understand how quantum physics works?
No, but I got used to it.